Reservoirs and bridges. Reservoirs and bridges. Reservoirs. Reservoir are the artificial lakes created by damming the river. Depending upon its purpose, reservoir can be storage reservoirs where water is stored to feed canal systems for irrigation and power generation. Food flood control reservoir which accommodate large volume of surplus water during peak flow times of a river. Surplus water is then released after the food flood abates. Distribution reservoirs are small storage reservoir which holds supplies for a water supply system for short spells of time for distribution of for drinking and other purpose in a regulated way. Investigation for reservoir site selection. There are a range of factors that influence the feasibility and economics of a proposed reservoir site. The most important of these is generally the location of the dam. After that, consideration must be taken to a runoff characteristics of the catchment area, the water tightness of a proposed reservoir basin, the stability of the valley site, the likely rate of sedimentation in a new reservoir, the quality of the water, and if it is to be a very large reservoir, the possibility of associated seismic activity. Once these factors have been exist, they must be weighted against the present land use and social factors. The purposes that the reservoir will serve must also be taken into account in such a survey. Topography. The area should be a wide natural valley, preferably ending in a narrow gorge where a barrier dam could be placed. This gives idea about the shape and size of the river valley, its stages of development and potential areas of scouring and erosion. Initial estimates of storage capacity can be made from topographic maps or aerial photographs, more accurate information being obtained where necessary from subsequent surveying. Catchment areas and drainage densities can also be determined from a maps and air photos. Reservoir volume can be estimated by planimetering areas upstream of the dam site for successive contours up to proposed top water level. Groundwater condition. Amount of leakage of water from the reservoir is controlled by the depth of water table. If the water table is so near the ground surface, the water level in reservoir doesn't rise above it. No serious loss by leakage will occur. On the other hand, if water table lies deep below the ground surface, the water table lies deep below the ground surface. The water level in the reservoir will stand above it and leakage will occur, the amount of which will depend on the permeability of the earth metal it rests upon. Permeability. During geological investigation, it is necessary to locate the highly permeable layers present in the reservoir area. The rocks, highly fissured, intensity joint, faulted, or have solution channels cause serious leakage from the reservoir. Generally, leakage will be more in rock dippings downstream than upstream. In some cases, ancient channels buried below the present valley floor, called buried valleys, often provide passage for profuse leakage of reservoir water. Sedimentation in reservoir. The amount of slate produced and supplied to a rivers depends mainly upon the lithological character and topography of the catchment area. The rivers flowing over the soft rocks and high gradient areas carry greater amount of slate. Reservoirs built on rivers which carry large amount of sediment may slip up very soon and its water storage capacity may be reduced considerably. Slit traps may be constructed upstream in such rivers to prevent siltation on reservoirs. In those areas where streams carry heavy sediment loads, the rates of sedimentation must be estimated accurately in order that the useful life of any proposed reservoir may be determined. Geology. The rocks exposed in the reservoir rim must be resistant to solution, erosion, and free of voids to stop leakage. If some potential leakage zones are present, it should be delineated. Highly jointed rocks should be investigated for joint intensity and spacing, which will help in assessing the grouting. Faults, if present, should be delineated since they require treatment, which may be expensive. Faults may be a passageway for water leakage as well as vulnerable or liable for earthquake effect. Movement on fault may initiate due to weight of water in the reservoir. If sand and gravel or water permeable bed are in the surface or vicinity of the proposed site, they may seriously affect the efficiency of reservoir. Palisation in competent art resistant rock like granite, quartzite, gneiss provide excellent site. Presence of shearing zone, water table, active faults and characteristics of rock in the subsurface are done applying geophysical techniques. Presence of weakened rock mass Presence of weakened rock mass or soil in the rim of the reservoir may be the cause of slumps or landslide into the reservoir. Increase in water level will further weaken them and hence cause slumping, increasing the stability and siltation problem. Before, after. Bridge. A bridge may be a bridge may be a bridge may be defined as a structure built over a river, a dry valley, or an depressed part of land to provide a link between the two opposite sides. The foundation of bridge piers and abutment requires a serious geological investigation. An ideal site for the construction of a bridge in is the An ideal site for the construction of a bridge is the one across the valley, cut in a sound rock and where the river flow is free from scouring due to bends, tributaries, and other causes. The chief factors which govern the stability of bridges are lateral forces, earthquake forces, and scouring action of river. Pressure from bridge and running water are the main lateral forces. Piers should be founded at depth, safe from scouring erosion. In many cases, the location of a bridge is decided more by socio-economic factors than geological considerations. In big cities divided by streams and rivers, a bridge has to be placed where necessary irrespective of subsurface geology. But in highways, there is often some flexibility available in the choice of placement of a bridge. In any major bridge bridge construction project, the bridge abutment and piers will be kept on sound, strong and stable rock foundation below as possible. The geological characters that need to be investigated and truly established are the depth of bedrock, nature of bedrock, structure of the bedrock. Depth of bedrock. Riverbed are covered by varying thickness of unconsolidated natural deposits of sand, gravels, and boulders not safe for foundation or of bridge pier. The piers placed directly on them will be unstable. The cover material is liable to be removed by scouring action of river. The piers will be placed on a stable foundation, preferably a rock under unsuitable thickness of cover material so that it is safe from the scour of the river. The height of the pier from under the span to the foundation level therefore depends on the depth of the bedrock below the river water. The depth of sound rock may vary from 5 to 20 meters in some to more than 100 meters in others. Drill holes are made all along the center line of the proposed bridge. Even on the banks sound rock sequence are reached. Utmost care has to be taken not to mistake the buried boulders for bedrocks. Boulders cannot be trusted as foundation for bridge piers. Height of individual piers may vary according to the depth of the sound bedrock below the surface, as is them should be founded on the stable rock. Nature of bedrock. Three types of loads are to be borne by the bridge pier foundation. The compressive vertical load due to weight of the bridge span and the pier material. The horizontal load due to thrust of the water flowing above has transmitted directly through the pier. The dynamic complex load, often inclined and sharing in character due to heavy traffic on the bridge. The bedrock selected as foundation for the pier must be strong enough to withstand some of all these loads throughout the life of the bridge. The nature of the bedrock is commonly determined by the study of petrological characters and engineering properties, especially the strength values, using the core samples obtained during drilling of test boreholes. Complete and useful geological profiles can be prepared all along the central line of the proposed bridge from the study of core logs. The core logs will give the complete sequence of the rocks below the surface material up to the desired depth. A decision to place the pier on a particular rock at a particular depth is matter of judgment and design requirement. Most igneous and massive sedimentary and metamorphic rocks like gneiss, quartzite are considered sound for bridge foundation. Weak rocks, which might behave badly in presence of water, include cavernous limestone, fractured sandstone, especially with clay cement shells, clay, slate, schist, and a layer of peat and compressive organic material. Presence of harder rock over weaker rock. Rock heterogeneity, zones of weathering, etc. are not favorable sites for bridge foundation which should be treated. Structures of the rock. Structures of the rock. Horizontal attitude and uniformly massive structure with depth are desirable characters on the foundation rocks as this offers resistance against failure. Even inclined rock in a confined situation are considered safe if they possess normal strength values. Folding and faulting might cause some uncertainty in establishing a perfect geological profile. Fracturing and highly joining is undesirable for the foundation as they might cause settlement beyond allowable limits. When bridge is aligned across the strike, various types of rocks with varying strengths may be encountered along the foundation, which necessitates a close examination of foundation rock under each pier and abutment. Fall zones are to be avoided and as the foundation as any further displacement along these planes will adversely affect the bridge. When bridge sites are located in zones of seismic activity, the foundations are required to be designed for additional seismic loads. In glaciated areas, care must be taken to establish the existence of drowned or buried valleys that might have been filled later. The occurrence of drowned valleys is considered one of the major complications in bridge foundation that limits the options of a design engineer. The factor of scour must never be overlooked as riverweed material and rocks under them at shallow depths are liable to removal by scouring. River valleys in mountain are subject to rapid erosion, hence bridge piers and abutments should be placed in safe areas. In plain areas, the meandering river have chances of frequenting the whole channel and hence render the bridge useless due to possible shift of the river course.